Thank you very much, first of all, for the invitation to do this very exciting science webinar and also giving me this very nice introduction before. I'm turning off my camera because sometimes we have some technical issues when the camera is on. That's why, in order to go through the slides better. Hello to everyone. I would like to welcome you all to this webinar. It is a pleasure to be here today and present this very hot topic of PFAS at the nanogram per kilo levels in food. I will start this webinar with a short background information about the complexity of the issue and how it is affecting the food sector. Then I will follow with a regulatory framework in food products, some analytical challenges that we're facing in the laboratory, our analytical approach, of course, and the method performance, and finally, some key messages to take home. Maybe you all know some just information of the background. PFAS are man-made chemicals containing at least one fully fluorinated methyl or methylene carbon atom composed of two classes. The non-polymers, which are polyfluorinated substances. A hydrogen is replaced by a fluorine on at least one carbon atom, but not all. And perfluorinated substances, where all the hydrogen atoms attached to a carbon atom are replaced by fluorine atoms. The second category comprises the polymers, which are fluoropolymers, polymeric fluoroethers, and the side chain fluorinated polymers. What is very interesting with these compounds is the strong bond of carbon and fluorine, which is leading to chemicals with very thermally and chemically stable, and today they are known as persistent, forever chemicals accumulative of, and of course, of safety concern. There are a lot of general uses of these compounds due to their interesting physicochemical properties, like fire-fighting foams. It is used also in cosmetics, in lubricants, in paints, in stain-resistant products, non-stick cookware, as we're using also at home, and of course in food packaging. But which are the main sources of PFAS in finished products? This is really multiple and complex. Packaging could be one of the entry points from plastics, inks, can coatings, and varnishes. And this latter, we are speaking more to non-direct food contact. Of course, equipment and delivery systems can be another entry point, like transport belts, gaskets, any O-rings, lubricants, and release agents. Water is also another source of PFAS entry, municipal drinking water, the processing water too, and discharge water. And finally, as they are environmental contaminants, they can come from any raw material, so from any animal-derived foods, fruits and vegetables, starchy root and tubers, and finally, we can find them in the infant foods. Earlier this year, there is a map that was published by Le Monde demonstrating the known contamination of PFAS in Europe. And here we can see it on the right with the red dots. We have more than 2,000 hotspots in Europe. It is impressive also to see the number of the blue dots demonstrating more the presumptive contamination of PFAS, and this is quite huge. Let's take a look now on the regulatory landscape. In August last year, the European Commission published a recommendation for the monitoring of PFAS in food, and in December the same year, the first European regulation was published amending maximum levels for certain substances and in certain foodstuffs. According to both documents, the member states should test for presence of four main compounds: PFOS, the perfluorooctane sulfonic acid; PFOA, the perfluorooctanoic acid; PFNA, the perfluoronanoic acid; and PFH6S, the perfluorohexane sulfonic acid. The targeted LOQs are proposed in order to make an exposure assessment. The indicative levels are proposed for root cause analysis in case that we have positive results. And finally, we have maximum levels which are established for compliance purposes for these four main compounds. Except for the four main compounds, according to the recommendation and the regulation, the member states should monitor, if possible, for the presence of 18 more PFAS. In the list, there contain carboxylic and sulfonic acids and also a sulfonamide. There are five emerging substances, and finally, some fluorotelomere alcohols and sulfonates. According to the European recommendation and the URL POPs guidance document for the determination of PFAS in food and feed, the lowest targeted LOQs for the four main compounds are for fruits and vegetables and also for food designated for infants and young children sold as ready to eat. And they're as low as 1 nanogram per kilo for the PFOA and PFNA, 2 nanogram per kilo for the PFOS, and 4 nanogram per kilo for the PFHXS. The indicative levels, which are the levels for root cause analysis in case of positive results, they're as low as at 5 to 15 nanogram per kilo for fruits and vegetables, except the wild fungi. And for baby food, they are for all compounds, for the four main compounds, are 50 nanogram per kilo. Now, from a more technical point of view, I would like also to show you some precautions to be taken in the lab in order to decrease some sources of contamination. We have two possible sources of contamination. One can be the sample preparation, and the second, the instrumentation used for the analysis. During the sample preparation, the use of ULCMS grade solvents is recommended due to their very high purity. Avoid glass and use preferably polypropylene labware, especially knowing that some of the PFAS can be absorbed on the glass. And this is have the opposite effect. It is more on the absorption we have a loss of the PFAS and not a background contamination. In case of an SPE apparatus use, make sure to not use any PTFE liners, but to have an alternative choice like us and stainless steel liners. Concerning the HPLC part, some adaptations are also recommended as the HPLC can be also a source of background contamination. So commercially, there are existing a lot of HPLC PFAS-free kits, and this includes PTFE tubings, caps, and filters that are replaced by a polypropylene ones. The installation also of a delay column between the pump and the autosampler in order to delay the PFAS present in the mobile phases. And again, the use of ULCMS grade solvent is preferably the best option for this analysis. As we need to analyze PFAS in the nanogram per kilo level, it is important to have a high-end sensitive instrument for targeted analysis. SAIX developed and commercialized a new MSMS system enabling lower LOQs, which comprises a new ion optics and a new source, as well as a new software. And this is the mass spectrometry used for the method development and validation of our analytical method. Now, concerning our method, we are having 57 analytes, including, of course, the four main compounds requested by the Europe with the targeted LOQs and MRLs, PFOS, PFOA, PFNA, and PFXS. We consider a more exhaustive list compared to the one of the Europe by including compounds already found in the FDA's list, compounds surveyed by some service laboratories in Europe, and compounds considered in recent peer review publications. In total, we have 10 different PFAS type that are included, and here you can see above the different categories and the number of compounds that are included in the different category. The method was recently published in the Journal of Food Additives and Contaminants in open access. And just to little bit summarize the procedure, we are having a 2 gram or 1 gram test portion, depending on the matrix, of course, which is supplemented by a mixture of 33 isotopically labeled internal standards prior to the sample preparation. Then we continue with an acetonitrile water extraction. We are adding some water and we control the pH with a phosphate buffer. Then we follow with solid phase extraction cleanup. And finally, before the LC-MS analysis, we are concentrated the final extract depending also on the matrix and the LOQs that are targeted. As it concerns now the method performance, we have 7 different categories that were chosen for method validation. We have baby food, milk-based infant formula, dairy products, infant cereals, fish, meat, eggs, oils, and fat. The first step was to check for the linearity. We have 7 calibration levels. In the validation process, we included 3 operators with 2 replicates and 2 spiking levels. For the step of the validation, we included, of course, a method blank, the solvents, of course, the unspiked sample, and 6 replicates of the sample spiked at LOQ level and 6 times at 5 times the LOQ level. Finally, we did a third step where we included a food commodity check in order to check the applicability of the method in the matrices of the same commodity group. And here we included the method blanks, also solvents, unspiked sample, and two replicates at the LOQ level. Acceptance criteria of accuracy, repeatability, and reproducibility were set according to the URL POPs guidance document for the PFAS analysis. The LOQs were matrix and compound dependent, and you can see them here on the table. The lowest one there for the baby food, infant formula, milk-based products, and infant cereals, followed by fish and meat, then the egg and coffee matrices, and finally the fish oil and vegetable oil and fats were the most complicated matrices. According to the URL POPs guidance document, the LOQ is the lowest successfully validated level of the analyte, for which it has been demonstrated that the respective criteria for identification, trueness, and precision are met. So I am insisting on the fact that we need actually to define the LOQ based on experimental data and not just only extrapolation from the signal to noise ratio. Recently, there are two scientific papers published already demonstrating the importance of this LOQ definition in order to give reliable results in the nanogram per kilo concentration level. Now, what about the performance of the method? The performance obtained for the four main compounds, PFOS, PFOA, PFNA, and PFHCXS, indicates the suitability of the method when the criterion of the reproducibility is set at 25%. When the criterion was defined at 20%, the performance passed at 5 times LOQ, whatever the matrix was, while two matrices did not at the LOQ level due to the slightly lower performance obtained, for example, in fish for PFOS and in full cream milk powder for the three compounds of the four, PFOA, PFOS, and PFNA. The LOQs for the matrices tested are presented in the table, and they are for baby food, infant formula, milk-based products, and infant cereals at 0.01 microgram per kilo, for fish and meat at 0.1, for eggs and coffee matrices at 0.3, and for fish oil and vegetable oils at 0.5 microgram per kilo. Now, for fish and meat and eggs matrices where there is a regulation, we achieve the lowest MRL according to the regulation. What about the performance for the remaining compounds that are included also in our scope? The method demonstrated adequate performance for the quantitative determination of all the other analytes, with only few exceptions that they're exhibiting indicators out of the criteria. Based on our set of data, whole X represents no difficulty in the analysis of PFAS as regard to the compounds included and also the analytical conditions tested. In contrast, we have some few analytes or performance characteristics that do not fit with the criteria of other matrices. Fish appears to be the most challenging one, with 8 and 4 compounds whose performance are out of the criteria at LOQ and 5 times the LOQ level, respectively. It is also worth to mention that the performance did not exhibit very significant differences between the group of the analytes that they are quantified with an isotopomer as internal standard and those determined based upon a derivative as a stable isotope label internal standard are there not all of them commercially available. The compounds are categorized in groups, and the LOQs achieved in the different matrices are shown in the table per matrix and per PFAS group. So here you can see which compound is included in which group and what is exactly the LOQ in the matrix validated. Knowing now that these compounds can be found everywhere, a big challenge is the background levels analyzed due to impurities found in regions, in the extraction cartridges, and in the laboratory instances used for the sample preparation. Here's an example of the PFOA. In the chromatograms here, we can see for the first one, the blank solvent, that there's no any signal of PFOA, but the same amount of PFOA can be found both in the region blank, which is a sample passing through the whole sample preparation without containing any matrix, and the beef sample that was analyzed at the same time. So here, in this case, we cannot confirm the presence of PFOA in the beef sample, as exactly the same amount it is found also in the region blank. So is it coming from the region blank or really the sample was contaminated? We did some trials in order to decrease this background contamination by taking these following precautions, decreasing, for example, the concentration of the internal standard used, because this is bringing also some concentration of the native analytes. Also, you use some high quality solvents. This also increased the price. We have, for example, for 1 liter of acetone in trial, that it costs around 500 Swiss francs. We avoided also the use of salts, buffer, and homogenizers. We conditioned very well the SP cartridges prior to use, and the SP manifold use we try to be as PFAS free possible without containing any Teflon. And in this case, we achieved to decrease the concentration of the region blank by a factor of 10. As you can see on the left, we have a concentration more or less to 3 to 5 nanogram per kilo, PPT. And when we are doing all this procedure in order to decrease it, we are around at 0.3 to 0.6 ppt nanogram per kilo. So now some key messages. It is very important to have a high-end instrument for achieving the nanogram per kilo levels in food, like the one that we used in our study, the SAIX 70500. It is mandatory also to control the background contamination for reliable data reporting. As I said, I insisted the LOQ must be based on experimental data and not only extrapolated from the signal to noise ratio. Like that, we are in accordance also with the URL POPs guidance document. Our approach is intended to ensure, of course, compliance with the European regulation, but also for investigation purposes. That's why we're including an extended scope of PFAS. The question now is, are there enough, the 57 analytes included in the scope? For the moment, there's no any international recognized standard, ISO, CEN, or AOC for food analysis so far. There's a new project opened at AOC level for the PFAS method officialization in June 2023, and Nestlé is a part of it. And like that, I would like to thank you all for your attention. I would like also Sykes for giving me the opportunity to present this webinar today. Of course, the Nestlé team that they are involved in this study. Thanks to Claudia, Bjorn, Antoine, Thierry, and Pascal.